This is the Amp Hour Podcast, recorded June 24th, 2012. Episode 101, with guest Matt Edis, Quality, Quadrature, Quidam.
Welcome to the Amp Hour. I'm Dave Jones from the EEV blog.
And I'm Chris Gamble of Chris Gamble's Analog Life.
And I'm Matt Edis of Edis Research.
Welcome, Matt.
Yes, welcome.
Thank you.
Thanks for coming on our show.
Sure.
Now, are you actually on our usual recording stuff, or are you actually using a software-defined radio to kind of beam in your signal right now?
Well, you know, we've got a wired network here at the office. I figure that's probably best for for something like this.
Yeah.
Yeah.
The oldie goldies, right there.
Mm-hmm. Because we found that wireless doesn't work very well. You know, everyone raves about wireless, but it just doesn't seem to hold up when we're doing streaming audio like this for some reason. It's a real pain in the butt. I don't know if you've found that, but we certainly have.
Yeah, well, you know, a lot of the consumer wireless stuff is designed, not for the levels of reliability that you might want when you're doing something like this. So, it might take more retransmits. If you're on UDP, you're not getting the retransmits and that sort of thing.
Okay.
Interesting.
And that's just audio. Imagine if we had to, do live streaming video. I don't think the technology's there yet to do, really good streaming video.
Well, the tack everybody seems to take is is really completely over provision. So if you need 5 megabits per second of video, you sort of give it the 30 megabits per second to make sure you'll be able to get everything through and have enough time for retries and stuff like that.
Interesting.
Exactly.
So how about a little background? I mean, you work on software-defined radio, but could you give us a little background on, where you come from, a little bit more about your company and what you're working on?
Sure. So I studied electrical engineering and computer science, and then after graduation, I came out to the Bay Area to work for Sun Microsystems, and I worked on UltraSpark 3. So I did microprocessors to start with, and then I moved on to a GPS startup, and after that a Bluetooth startup. And it was while I was at the Bluetooth chip startup that I was that I discovered the GNU Radio project, which had been started by Eric Blossom in very early 2001, as I recall. And the GNU Radio project was a free software, software-defined radio project, to build essentially a framework for software-defined radio. And so I discovered this and joined up, and we did a lot of really interesting applications. Early on, we started off with things like FM radio and sort of ham radio bandwidth stuff through sound cards and things like that. And eventually, we moved on to and did the basically the first open HDTV receiver, and that was done. I think that was 2002. It might have been 2003, but we did. So it was an HDTV receiver, and it wasn't real time, but we could record samples off the air and then post-process them and to get the MPEG output, and we put the MPEG output through Zine, as I recall, and watched a part of an episode of Law and Order, which is the thing you're most likely to find if you record TV at a random time.
That's right, yeah. It's a stochastic thing, right?
Yeah. It's like the sun never sets on the British Empire. There's always a broadcast at any time of Law and Order, and so that was the first thing we got.
I imagine someday, they're going to beam, some really high power signal into space, and then, millions of light years later, the first thing an alien civilization will hear is that.
Dun, dun. Yep.
Yeah.
No, come on, it's Hitler. Haven't you seen Contact? Haven't you read
No,
Contact?
I know,
right.
yeah.
Yes.
I'm just saying when we really crank the signal,
Right. Oh, boy. So you joined two startups there, Novariant and Zevo.
Yes.
If I'm pronouncing those correctly. Was that a conscious decision to go for startups?
Yeah. So while I was at Sun, so Sun was my first real job out of school. I had interned when I had been in school, but I got to Sun, and it was a good company. But overall, the experience taught me that I didn't want to be at a huge company, and that I wanted to.
Why is that?
Well, there's a lot of stuff that goes with being a huge company.
Dilbert.
Yeah, there were the Dilbert
Too
moments.
much Dilbert style management.
There was a good amount of that, but there's also at a large company they're able to say, okay, you do X, where X is something extremely specific, and I really always thought of myself as a generalist, and so. So when I found this GPS startup, I got to today it's called Novariant. At the time, it was called Integranautics, which was an even worse name, to be honest, because we ended up spelling it a lot.
Yeah.
How do you spell that? Yeah. So we had that happen a lot. But that was a lot of fun because I got to work on RF stuff. I got to do GPS. We did controls. So our technology was used to land airplanes, drive farm tractors. We were tracking jockeys and race cars and things like that. So it was all sorts of stuff. And I got to do all sorts of interesting things, including actually drive tractors, which is fun for a little while. Although that was part of why I decided to move on from there. I found myself spending quite a bit of time on tractors.
I've hit a low point in my career. I'm driving a tractor.
Yeah, pretty much. I mean, it was a great learning experience.
Oh, boy, right. So you just moved on to a second startup. You liked it so much that you decided to do it again.
Yeah, so I went to, I mean, it's sort of the thing to do in the Valley, right? I mean, people sort of, it's like migrant farmers, but for engineering.
Right,
And so I moved on to a different, different startup to do Bluetooth chips. And this one was a little bigger. Novariant was about 20, maybe less than 20 people while I was there. And the Bluetooth chip company was between 70 and 100. So it was
that's
a
decent sized company.
It was more of a classical startup.
Yeah.
Yeah, it was sort of the classical venture funded style startup. And, learned a lot there, got to work on a lot of different stuff, this time on, ASIC design. So I did a lot of signal processing and system architecture work, on a Bluetooth chip. And so that was that was interesting.
So why did you make the conscious decision to leave there and form Edis Research, actually do your own company? Or was it did you make the big leap? Right, I'm going to quit my job and I'm going to form my own company and then earn nothing for the first year? Or did it slowly build up to a point where you had to leave or it made sense to leave
the ramen diet and everything else that goes with it,
right?
Well, it was kind of interesting. So, I had mentioned that I had started with the GNU Radio project in 2001, and I was at the Bluetooth chip company from 2001 2004 when I left. And so, we did a lot of interesting stuff with GNU Radio, but we found it very limited because there was no interesting hardware, right? Like when we were doing the HDTV reception, that was done with a $1,500 data acquisition card.
Oof.
And a TV tuner evaluation board from a company that had actually already gone out of, or had already canceled that program and had been acquired by another company and wasn't supporting it anymore. So there really was no interesting hardware, and so I. And this was a hobby project. It was, evenings and weekends and stuff for me. And so I said, well, what would I want in a software radio? And I sort of, came up with a block diagram and then slowly fleshed that out. And that's what eventually became the USRP. But, this was still 2003. And for the longest time, I tried to convince somebody else to make this thing because I didn't want to make it. I wanted to use it. I wanted to play with it. And, I wanted to do MIMO and, wide bandwidth stuff and do signal processing in the FPGA and all that sort of thing. And there was no practical way to do that for less than tens of thousands of dollars. And so I went around to companies and I begged them to make it.
Right, so you were more fascinated with the software and DSP side than the, hardware was like almost a pain in the ass. It's like, oh, do I have to build it? Why can't I just buy it? Is that the...
Yeah. I mean, yeah, that's pretty much how it was. And so I tried to convince somebody else to make it. Nobody would. And so I built it myself, but this was still an evenings and weekends project. And, people on the GNU Radio mailing list were like, oh, well, I want one too. And, it sort of,
of course,
and
Right.
it sort of went from there. And I was able to, I was very reluctant to quit the day job and sort of start the company. And so I was very lucky. Some people involved with GNU Radio were able to hook us up with some people at NSF and the University of Utah. And I was able to get some consulting work to support GNU Radio and USRP, under contract. And that's how I knew, I'd be able to, pay the mortgage if I quit the day job.
Yeah, right.
And so I did that. And even at that point, so this was September of 2004. Even at that point, I did not want to be selling these. The goal was I wouldn't sell them. I would just support them. And all the other options for somebody selling them really fell through. And so I sort of reluctantly did it myself. In retrospect, it worked out really well, and I'm glad and very lucky.
I guess that's the downside of software-defined radio in the first place. Is most people who want to do software-defined radio are software people, and so eventually you have to have someone jump in and do it, right? You'll kind of take that step backwards and touch your nose. And
I mean, I really consider myself sort of a signal processing and communications guy. But you can't just stick the antenna into your USB port. You need something in between, and I had to make that.
Yeah, damn, it doesn't fit.
Yeah. I needed the USB to SMA adapter.
Yep, yeah, and that's what you built, really. Right?
Yeah, right.
So can you tell us a little bit about the first ones? Because I mean, I'm looking at edis.com right now, and that's ETTUS for listeners who don't want to visit our site for whatever reason. And these things they're pretty slick. I mean, they're not huge boxes right now. They look like they're maybe 3-4 inches square and maybe an inch high. I mean, they look compact. And so can you tell us about how it started? Because I'm really guessing it didn't start looking this slick.
So we started with the USRP, which later became the USRP 1, so that to differentiate it from the future products. It actually is still being sold in much the same form. It didn't have an enclosure at the time, and we didn't have this big selection of daughters, but the USRP. The original USRP was much like it is now. So it's, by today's standards, small FPGA, the USB 2.0 interface, and the A to Ds and D to As, and then the two connectors for the RF daughter boards. And so at that point, I basically, I was shipping bare boards to people, and a power supply and a USB cable. And eventually we designed an enclosure for it and more daughter boards. The newer device is the sort of second generation stuff, which is most of what you see on the web page is the stuff in sort of the off-white enclosure color. That at that point that was it was. I already knew it wasn't going to be just a hobby, and this wasn't just a side thing. At that point, it was a business, and more of the customers were not hobbyists, and so we wanted the professional looking enclosure and all that stuff. But certainly the block diagram between.
Were you a hardware designer at that point? I mean, when did you start considering yourself a hardware designer? Still,
well,
no.
So that's sort of a distinction. I don't know if I necessarily make. I mean, it's more of a I've sort of always done hardware. I've always done software, but really I like being in the comms systems area. So if it's software for that, if it's hardware for that, they were both interesting. I mean, I started off, before college and all that, I was a ham radio operator or a ham radio designer. I wasn't much of a sort of get on the air and chat kind of guy. I was more of I build it, talk to a guy, prove it works, move on kind of thing. But so I always had this communications and RF focus to the hardware. Obviously, my time building microprocessors for Sun was a little bit of a diversion from that. But other than that, I've mostly been around communication systems.
And how long did you go for just working on your own before you sort of expanded the empire?
So,
or is it still a one-man band operation?
No.
Is it still the Midnight Engineer?
It's not huge, but it was just me for the first year and a half, and then at that point I said, okay, I can't design more stuff if I'm packing the boxes myself. So I would hire people off of Craigslist to pack boxes, and they tended not to last very long. They would sort of move on. So it was all temporary people. It was in my house, right? I mean, I was I used my garage for storage, and like the sunroom was my office.
This is great.
And the dining room table for packing stuff. And so about 2.5 years in was when I decided, okay, it's time to get an actual office. So I got an office that was about a block away from the house, which was really in more of a sort of doctor's offices kind of complex. So like a dentist might have been in this sort of office. So it was about 700 square feet. And then about 6 months into that, so about 3 years in, was when I first hired an actual, formal employee to do on a regular basis the sort of bookkeeping and shipping and stuff. And then about 9 months after that, so about 3.5, 4 years in, was when I've hired my first sort of full-time engineer. And so today we're at about 7.5 years since we started. We're in the third office, if you count my home as the first.
Well, you have to for historical purposes.
Right. Yeah,
the HP garage counts as an office, right, for the HP guys. So
yeah, true, very, very true.
The Edda's sunroom,
Yeah, well, now it's back to the guest room, and so we have 12 people who are Edda's research employees, and 2 of those are based in Austin, where our parent company, National Instruments, is based, and the other 10 are here. We were acquired in 2010 by National Instruments, so it's about 2.5 years since then.
That's great. Yeah, and that's actually how we found out about you.
I've got a little side question. I was going to talk about this more in general on the show later, but I think I'll bring it up now. Is it so these people actually work on the premises? They work in the office?
Yeah. So we have 10 people in our physical office here, and then 2 people in Austin who are at NI's actual main campus.
Right. Okay.
But the other 10 are all here, and then I've always had. I mean, even when it was just me as a full-time employee, I always had a sort of 2 to 3 to 4 consultants who would do. I would sort of parcel out pieces of the projects to them. So even now we have 3 or 4 consultants who will range between, maybe 10% time with us up to 50, 60% time when a particular project is busy.
Got it. Because that was going to be my question, was that if you're doing a startup these days, how important is it? Or if you're forming a company or whatever, I hate, this term startups used too often, but how important is it to actually have people on site? Are you better off just not leasing a big premises or not buying a big premises and having everyone work from home and trusting them, and almost like, even if they're full-time employees, still have them from home? Or is it better to actually have them in the office where you can crack the whip and manage them?
So I've always, in particular for hardware design and full-time employees, that sort of stuff, I've always leaned towards having people on site. So I think there's no real substitute for being in the same place. But that being said, there's
right.
A lot of people have made it work. Certainly software is easier to do remotely.
Yeah, exactly.
I actually, back when I was looking for that first full-time person part-time person to do shipping, had a number of people say they wanted to do shipping by telecommute, and I didn't understand how that would work, but they insisted they could do it.
I'll take all your inventory.
Yeah.
You just, we'll lock my front door at night, and then I'll just ship it out when you need me to.
Yeah,
it's fine.
That's pretty much what they wanted to do. But no, in general, I've always leaned towards having people in the same place.
Right.
I think it's just a much higher communication bandwidth, and especially with test equipment and things like that, it's really helpful to be in the same place.
Oh yeah, with RF stuff. Oh my god,
with RF stuff, you can't exactly equip your own lab with high end.
Did you have
gear.
to rent stuff? Like, is that mostly how you did it, or did you actually have stuff from your own hobbies, or how did you actually get started with that kind of stuff? Because we've talked to Jeff about that. We know from just looking at test equipment ourselves. How do you do an RF startup, right? I mean, or RF company to begin with, because you need so much stuff. I mean, I know you were building radios, but you got to calibrate them at some point, right?
Yeah, and even when you're building radios, you have to have other people's equipment to test them. Otherwise, you can't trust anything, right? You have to have the independent verification.
Right.
But when I first started, I had, even as a hobbyist, I had accumulated a lot of sort of Hamfest specials. So I had some really old, stuff. I mean, I had a spectrum analyzer that probably weighed about 75
we need model
pounds.
numbers here. We need model numbers, Matt. We got to hear it.
We have a technical audience here.
I think it was the HP. I think it was 714 or 741 spectrum analyzer with the 8555 plug-in that actually went up to 18 gigahertz, but anything at sort of 2 would show up at 4, 6, 8, 10. So you had to sort of know where it was. Where the signal was, but
right.
There is a signal here somewhere.
Yeah, so I had that, and then after a few months of consulting, I was able to, and through this contract with the NSF, I was able to get some heavily used through eBay, slightly newer generation stuff, and over the years we sort of always, buying new test equipment, it's like buying a new Mercedes. You drive it off the lot, and the value goes down. So I've always sort of mostly bought stuff off of eBay, and then now they're a part of National Instruments. A good deal on their stuff, and so we use a lot of that.
I'd hope so.
Although not as good a deal as you think, but better than than outside. And so
you get the 40% discount or whatever. Right?
Yeah, so we end up using a lot of that, the
margin,
and but. I mean, early on, it was all very low cost. Make do with what you can. Rather than a phase noise meter, use a spectrum analyzer and tape data by hand. It didn't have all the conveniences.
Wow. So was it mostly spectrum analyzer, or was that? I mean, that was the main thing. Like VNAs or anything like that.
The three big tools for me are the spectrum analyzer, the signal generator, and the logic analyzer because of the FPGA work. And oscilloscopes are useful too for power supplies and things, but sort of those aren't too expensive. You can get something reasonable there. But the big three are the signal generator, spectrum analyzer, and logic analyzer.
Yeah, and these days logic analyzers, you can push a lot of that stuff on chip. So, but I mean, 2004, it was a little different. I mean,
yeah.
So what were you? What were some of your first FPGAs? Because I mean, so. We can actually see on the Wikipedia page about this, which is cool. There's, your hardware's on Wikipedia. That's pretty cool to start with.
Yeah.
It says it was Spartan 3A DSP. So, I mean, what was it like? I mean, was that kind of top of the line at the time? What was it? I mean, Spartan isn't Vertex, right? So.
Yeah, no, Spartan is the basic range back then.
Right, so the original USRP, which, and again, is still available in this form, that was based on a Cyclone from Altera. And a Cyclone 1, and I think they're on like Cyclone 4 or 5 right now.
I was going to say Cyclone 1, yeah.
And so,
okay. I was looking at the N200.
Yeah, that's the second generation device. The first generation one was the Cyclone 1, which was I chose that particular one for one very specific reason, which was that it had the most pins of any FPGA that was not in a ball grid package. And because I wanted
QFP 240,
and I wanted to do, it was still a hobby thing at that point, and I wanted to be able to do rework and stuff by hand. I had to, and I knew I couldn't do that with a BGA, so I got the biggest FPGA you could get without a ball grid, and so that's how I chose that particular Cyclone, which has no multipliers. So we had to do a lot of interesting DSP algorithms to avoid, since there's no hard multiplier in it. You either had to use a lot of logic fabric to create a multiplier,
which it didn't have much of,
right? Very much, or come up with algorithms that did not require that. And so that's what we did back
Interesting.
then. And then since then, we've moved on. The second generation stuff is all based around Spartan 3 and Spartan 3 DSP, which is at least, have
It's got a lot
hard
of Macs,
DSPs
right?
in them and multiply accumulate units in the newer ones. And those and are ball grid
Why
now.
the switch from Altera to Xilinx?
Well, so the Altera choice in the first place was made again entirely based on that pin out.
Based on package,
The switch to Altera, the switch to Xilinx was partially. Xilinx just tends to be a lot bigger in the comms, whereas I think Altera is sort of bigger in networking and other spaces.
Yeah.
But and also while I was making Altera based devices, I would sort of weekly get somebody. Oh, do you have a Xilinx based device? But in the entire time I've been making Xilinx based devices, I've only had one person ask for an Altera. And so I think if I was making a box that was completely closed and the user didn't need to modify the FPGA, I would consider Altera, I would consider Xilinx, I would even consider Lattice. But since my users want to modify the FPGA and they want to do it in tools they're familiar with, I need to give them the Xilinx chip that they're expecting.
What you should do is you should say, well, I'm going to design in whatever chip I want. You have to buy a $50,000 seat of simplicity, and then you can target any of them. That's your solution. I mean,
But the good thing now is that all of the manufacturers basically have free tools for everything but the extreme high end. Right?
And at the time, they're Altera had you could have a free tool or you could have the Linux based tool, but you had to pay for the Linux based one. And so I've always, they've all sort of been very weird about it, how they, operate that.
Mm-hmm.
I've tried to be sensitive that, okay, we're selling somebody, hardware for like $700. If they have to spend $3,000 to program the FPGA, that's probably a non-starter.
Yeah.
And so that's also part of how we chose the FPGAs. So the particular Spartans that we chose from Xilinx are chosen so that at least in the smaller version, you can at least use the free tools. So that's part of why there's an N200 and an N210. The N210 has the big FPGA. Yeah. The N200 has the one that you can program without buying the tools.
All right.
Oh, interesting. Very interesting.
Nice.
And so so it's got a lot of other interesting hardware on here as well. I mean, you don't it doesn't say the brand of the A to Ds and the D to As on there, but obviously those are higher end chips. So what kind of went into that hardware decision when you're looking at those?
So
is that mostly cost?
On the original USERP 1, we found there was this great chip from Analog Devices that has both the dual A to D and dual D to A in one package. And that's why if you look at the USERP 1 board, there's very little on the board because there's this one highly integrated chip. But for the newer devices, or the N series in particular, we moved away from that because although it's nice and low cost and highly integrated, there isn't a sort of a higher sampling rate, higher precision version of it. So if you look at the N series, it has a lot more individual chips. It has a separate A to D and D to A converters. It has low speed A to Ds and D to As, which also were included in that one chip on the other device. So where one chip on the USERP 1 became 6 chips on the USERP 2 and N series. And so it's a lot less integrated and a lot more pins as well, which is also the main reason why the original USERP 1 was two-way MIMO in the box, as it came. And the newer generation, we've moved to one antenna per motherboard, simply because there's just so many more pins when you have the higher end converters that it's not as practical to put two on one board. And so to do MIMO, you take multiple boards and tie them together.
So could you explain for our audience what MIMO is? Because that always confused me when I started learning about it.
Sure.
Maybe just a really quick rundown on it.
Sure. So the idea is that MIMO stands for multiple input, multiple output, and it's actually a term that comes from the old control systems days. But the idea is that you have more than one transmitter typically and more than one receiver. So people will come up with sort of in between terms like MISO and SIMO, but it's silly.
Right.
Basically, so when somebody says 2x2 MIMO, it means there's 2 transmitters and 2 receivers, and the reason for that is that you get diversity out of having more than one transmitter and out of having more than one receiver. So if, for example, if one receive antenna happens to be in a fade because of the particular position it's in, as long as you space the other antenna far enough away, its probability of also being in a fade is uncorrelated, and so the chances of both being in a fade is pretty low, and so you get more reliability. And with higher order signal processing, you can do more interesting extensions on that, but it's all basically the same concept, which is you get higher reliability, which you can trade off for either lower power or more bit rate or something of the like, based on having more antennas. And so like 802.11n went to 2x2, 3x3, and I think they do 4x4 in some situations. And and like 802.11ac.
That's why you see routers now having like multiple antennas as well, right?
Exactly.
They got dual diversities and wireless mics and things like that. All of your professional high-end wireless microphones, for example, will have a dual diversity antenna on it, so that as you walk around, because your transmitting source is always moving. I.e. the person, the microphone's attached to someone, then there's the chance of those dropouts happening is quite large if you've only got the single antenna. So if you've got that dual diversity one, then I guess it can eliminate that, but not entirely. How much scaling do you get? How much reliability scaling do you get by going from 2 to 3 or 4, for example? Is there a rule of thumb there? Or?
Well, in the case of the wireless microphones, that's a very simple form of MIMO. That's sort of the original one that's actually been around a long time. And then the full MIMO, so like when you have an 802.11 or a USERP or something doing MIMO, that's actually typically doing a receive on both antennas at once, whereas the wireless microphones will switch. But you get like most things, there's a diminishing return. So you get the bulk of the bulk of the improvement from the first couple of antennas you add, and then after that you start to have get to impractical limits. So for example, 802.11ac I think is going up to 8 antennas, but it's not like you go from 8 antennas doesn't really give you even as much improvement over 4 as 4 gave you over 2, right? It's diminishing returns. So, and at some point it's just impractical, right? You're not going to have 16 antennas in your cell phone because they're not useful unless they're at least spaced far enough apart physically. And a cell phone is only a certain size, so you're not going to see 8x8 MIMO in a cell phone. I don't think, because just because it's not practical size wise.
But what about maybe in a Pico? What are those called? The Pico base stations.
Cells and the base stations. So the base stations that's where you will see the 8-way take off. I don't 16-way may be pushing it, except for sort of specialized defense applications. But you will see. I think a lot of cell phone base stations now are 4-way, and I think you'll see them go to 8-way without too much trouble, because they're not as space constrained as your pocket is.
So what about the? So does the USRP does that work on like the different 3G, 4G bands? I mean, can you use an Edis product to actually look at network traffic and actually capture it and try and decode it from cell phone towers and stuff like that?
Yeah. So actually, I mean, you should really think of the USRP hardware as really that antenna to USB or antenna to gigabit Ethernet adapter. So what you can do with it really only depends on the capabilities of the FPGA and the processor speed in the host computer, for the most part. So we have people. There's a project called OpenBTS where they built a complete GSM base station stack around the USRP. And so there are actually active GSM base stations typically in sort of very remote locations, running on USRPs. So they've been used at Burning Man, were some of the first public demos, where they're not very far away from any other cellular towers, and so they were this project, this OpenBTS, allows you to create a GSM cell phone network. And so that's a 2G standard, 2.5G, depending who how you count, or which marketing person you listen to. But people have used our hardware on Edge and GPRS and UMTS, and so and as well as CDMA. And so we know of people doing most of the 3G standards with our hardware. They're not released publicly, unfortunately. But people.
Yeah, I was going to ask about the legality of that. I mean, what are the implications of that because of the FCC regulation and even just the pesky cell phone companies kind of protecting their turf?
Well, right. Well, there's all sorts of all sorts of legalities there. There's in terms of transmitting on cell phone bands. If you're going to set up an OpenBTS base station and do that, you need legally you need licenses from the FCC, and if you just sort of download the software, set it up, you'll be stomping on like AT&T or something, and people's cell phone. If you don't set it up right, people's cell phones will try and talk to your base station instead of the public the base station that they want to be talking to, and so. There's all sorts of rules, and it's a mishmash. It really depends on what band you're in, what country you're in, and so our hardware is type certified as test equipment with the FCC. But if you're going to transmit, you need the appropriate licenses. Use it on ham bands, you would need a ham license, and you would need to follow the ham rules. If you were to use it, as a cell phone base station, you need the appropriate license for that. Satellites, no matter what you use it for, unless you're receiving only, you're typically going to need some form of license.
Okay. Well, that's interesting because it could be used in those ways. I mean, have you seen any problems with that yet or in the future? Because I could see, effectively, with so much stuff moving to 3G, 4G service for tablets and cell phones and everything else. I mean, people do man-in-the-middle attacks for networks right now. It's conceivable they could do the exact same thing for cell phone networks, right? I mean, you're just a different piece of hardware.
Oh yeah, and people have demonstrated man-in-the-middle cell phone attacks with our hardware. There was, I think it was at DEF CON or maybe it was Black Hat.
Oh, that's right. And I think Ryan told me about that.
Yeah, that was Chris Paget demonstrated that, and that used basically that was a demonstration of how insecure the cell phone network is, because they used OpenBTS, and everybody's cell phone in the audience would camp with their base station instead of the AT&T base station. And their base station just said, iPhones, "Hey, I'm from AT&T, right?" And so, and they
give me your
play
data
man in the middle all day long. And so the newer standards are a little better than GSM was, but really not as much better as you'd hope. And really, so I mean, Eric Blossom started the New Radio project in the first place. That was one of his goals, was to demonstrate how insecure all these networks were. And so our users have ended up doing that, but there's all sorts of and one of the big applications for our hardware is demonstrating how a lot of these specialized networks are insecure, whether it's whether it's GSM or the tire pressure sensors in your car, which are now wireless on new cars, or whether it's pacemakers, wirelessly controlled pacemakers are insecure, and that was demonstrated in using USRPs. So there's a lot. I mean, wireless security it has really been neglected. So that's one of the big applications people have used our hardware for.
Has anyone mounted one to a quadcopter yet? Because that's just the first thing my mind jumps to. I know that's just a dream of mine, I suppose, because that would be doing both.
Yeah. So about 6 months ago, there was a group that put USRP and essentially the man-in-the-middle attack system that Chris Paget had demonstrated and put it in it wasn't a quadcopter, but it was a UAV.
Oh, yeah?
It was really
Okay.
a remote controlled airplane.
Okay.
And flew it and demonstrated that you could intercept GSM, cell phone calls remotely by flying a model airplane over.
Wow.
And it was profiled in, it was either Popular Science or Popular Mechanics.
Yeah.
There was sort of like a half pager on it. And I mean, it's a neat application, and we know the bad guys are doing it. We know governments are doing it.
Yeah.
And now we had some hobbyists demonstrating it.
Yeah. Dave dropped out, unfortunately, of our call here, but he would be he would love to go into his conspiracy theories. I'm not sure what happened to his network, unfortunately, but
maybe the bad guys got to his
maybe
network.
maybe yeah he's been spouting a lot lately. Hope he hears that later. We love you, Dave. So I wanted to ask just kind of about the technical side of it too, because. So I've done a little bit of RF stuff. I used to work on an RF system that when we actually crunched down in an FPGA similarly. But is it like you mentioned at the beginning? You were collecting all this data for HDTV stuff, right? And then you actually had this big chunk of data, and then you used a computer to process on it, right? Mm-hmm. Are you still doing that now, or actually are you pipelining it through the FPGA where you actually have the algorithms in the FPGA doing the DSP in there now?
Right. So the goal is always, for us at least, is real-time processing.
Okay.
And so that can be a combination of FPGA processing and host computer. We do have, for some applications, it's not a big deal, right? So if you're in a receive-only application, you can just receive and process it offline, and if it takes longer, your Law and Order episode is a little bit delayed. But
right.
But if you're
done.
Exactly. But if you're doing a two-way communication system, you really want it to be real time. And so computers are obviously getting faster. Multi-cores are of course a big part of that. And GNU Radio and our drivers and everything that all the software that we use is all multi-threaded, and it really does parallelize pretty well. Okay. So more cores typically does speed up your applications. But for certain things, you just want to do it in the FPGA because it's not just a question of speed, which the FPGA can be faster in some on certain types of computations, but it's also it's typically going to be lower latency and more reliable latency in the sort of real time sense. Right. And so the direction we've sort of headed with our hardware is that we provide a baseline FPGA image that has the sort of modulation independent stuff. So sample rate conversion, frequency translation, and that sort of thing to get the samples in and out of the computer, and then you do most of the interesting processing on the host. And then if people find that the host computer is not fast enough for their application, then we suggest, okay, then you might want to look at offloading the processing to the FPGA. For a lot of applications, and of course more and more all the time, a plain old laptop is more than enough. So today, this was back in 2002, we were doing the HDTV. Today you can make your laptop do the real-time HDTV. And so sometimes it's just like, well, just wait for your processor to get fast enough. And sometimes, well, if you can't do that, then you offload to the FPGA. The FPGA is, of course, harder to program, but we're working on making that easier for both. But that's a big task. And so it's a more specialized skill set, and it's a more developer time intensive process. So
right, and then it kind of moves out of the SDR, right? Because that's software defined radio. It'd be more like EDR, like for embedded defined radio, right? And you actually have a series for that. Also, I was looking down the wiki page and I see that you actually have an onboard OMAP, which you can actually push stuff to that then, right? Yeah,
so there's basically three series of products we have. We have the USB-based series, which sends samples to a host computer USB. There's the networked series, which sends the samples over gigabit Ethernet to the host computer. And the embedded device, the host computer is in the box. So the host computer runs Linux on this OMAP module from Gumsticks, if you're familiar with them.
Nope.
So it runs Linux on this OMAP processor, which has an ARM Cortex chip, and it runs the same software as if you were running it on your laptop. It of course runs it a little bit slower because it's not going to be as fast as your laptop. But that's in the box. So that kind of so if you have one of those, you don't need the external computer. You just you sort of attach power and attach an antenna, and you have the radio.
Yeah.
And
plus you don't have to squeeze it down through an interface. Even fast interfaces sometimes can slow down, right? USB 2.0, even gigabit can have collisions, right?
Right. So
all that
this
stuff
one is
on board is a little faster.
Yeah. So in this one, the FPGA is directly on the bus of the processor. I mean, now the bus of that processor is roughly the speed of USB 2.0. But
that's true.
So the advantage of that is not the speed. The advantage of that one is sort of that it's this embedded form factor, and you don't have to have an external laptop, to go with it. And so that one actually also happens to have a TI DSP on the chip, on the TI OMAP. And some of our customers have taken advantage of that. Again, it's a little bit easier to use than the FPGA, but it's not quite as easy to use as the host processor. So there's sort of this continuum from really easy to use host processors, but somewhat slower than the others, up through harder to use until you get to the FPGA, which is, takes it has a learning curve to it, but it can be the fastest option. So are you willing to spend programmer time or execution time is really the question.
Okay. No, that's good that you have all those options there. I saw today that Xilinx actually just announced a kit today. I don't know if you saw in the comments list on the discuss.theamphour.com. But they actually put their, they've got their embedded system now too. That new processor they're doing, the Zinc, they've got like logic around it, and then they actually just popped an ADI chip off of that. And so that's kind of the same thing as your embedded thing. I think they they have, so then you'd write code for the hard coded processor in there. You'd be able to put your fancy DSP stuff around it, and push it out to the hardware after the ADC and DAC stuff after that. So yeah, it's the same kind of idea, but theirs is a hell of a lot more expensive, I think, too. Because what kind of prices are you guys talking about here?
Well, so our devices start. You can get a full up set at I think around $700 or so. So
awesome.
That's the bus based device, and if you get the embedded devices, that it's sort of $1,300 kind of range plus a daughter board. So we have products. You can start out and do interesting things from $600 or so up to about $2,000 for the high end, and we're of course working on a bunch of new products that will continue to expand the range in both directions on that, and extend the capabilities. We have the next generation embedded device coming, which will be smaller, better, all that stuff. And we definitely see embedded as a very interesting direction.
Yeah, I love that stuff personally. I think it's. I mean, I can't write software for crap, but I think in terms of the processing, when you don't have to attach it to a computer, that's really cool. But obviously that throws in a whole lot of other stuff in there, and even the prices. I mean, the prices are. That sounds high if you just start stepping into it, right? But then you think about, well, people are paying this much for 3D printers these days. They pay that much for UAVs. It's not. It's definitely what's that term called? It's not. It's something above hobbyist. It's like some mashup of hobbyist and professional. I forget what it is.
In cameras, they tend to call it like prosumer or something like that.
That's it. Oh, that's the one. Sorry, I wasn't even close, was I? Yeah, prosumer. That's what I was thinking of. So mid-range like cameras. I always hear prosumer about cameras and stuff like that. So that definitely seems to fit.
Yeah, well, I came at this really from the direction of the hobbyist. I work as an engineer, but my interest started from the hobbyist direction. I really did. So I've tried to, always have offerings in the range that are reasonable for someone who's a hobbyist, and it's, there's no big company paying the bill when it comes. And so we've tried to always keep, something in that range. Obviously, as we add more capabilities to the, and have the sort of the higher end devices, the prices will go up from there. But we will always keep something in the hobbyist range, because that's a near and dear to my heart part of the for this.
Yeah, and it's good business too. I mean, it helps bring people in, gets them acquainted with your company and all the software that's available for it. So, could you explain the daughterboard concept? Because we actually had a question in the discussion server about that. What did they say? So, why do they all have a single daughterboard slot? The original USRP one was the only one with 2 and UHD support, and now it seems to be lacking some essential features like hardware timestamps. What's the rationale behind that?
Okay, so there's a few questions there. I'll start with what the daughterboard is. So the model was always that we wanted to be able to cover all sorts of different RF bands, whether it's the 2.4 gigahertz Wi-Fi bands or the 5 gigahertz Wi-Fi or 400 megahertz, land mobile radio and ham radio. There's a whole wide RF spectrum, and at reasonable cost, it's hard to get huge swaths of that in one piece of hardware. Right. And so instead, we did the baseband on the motherboard device, so like the USRP 1 or the USRP 2 or the N210, that's the motherboard. And that has the A to D and D to A converters through the interface to the computer. And then the RF side, the part that takes that baseband and translates it to, let's say 700 megahertz or whatever, that's done by the daughterboard. And so the daughterboard plugs on, and it's basically if you're a ham, the daughterboard is a transverter. It up converts the baseband to RF on transmit and down converts it on receive. And it'll have the filters and the amplifiers and that sort of stuff. So it's the RF front end for the device. And so they're interchangeable so that, you could pick the ones for the bands that you're interested in. So when we first started out, the technology was such that for a reasonable performance, reasonable price daughterboards, they had relatively narrow ranges. So they might be, one board was 400 meg to 500 meg, and one board was 800 meg to 1,000 meg. And our newer stuff is getting wider and wider band because there's more integrated chips that cover wider bands. So our newer daughterboards will cover, like there's one that covers 50 megahertz to 2.2 gigahertz. And there's one that covers 400 meg to 4.4 gigahertz. So as these get wider and wider band, there's less and less need to interchange them. But, there's no, at least not yet, we don't have the sort of DC to 6 gigahertz coverage that we'd like. But once we can get to that at a reasonable price and reasonable performance, at that point they won't need to be interchangeable anymore. Right.
Well, and that's the problem too, because by the time, basically at that point you're playing almost off the shelf stuff, right? Because that plays to the affordability, right. And by that point, people are going to start asking for 10 gigahertz or something else too, right? Because that's just how technology seems to go. So
right. It's ever expanding. Yeah. So that's the daughterboards. The original USRP one, the person asking the question is correct. The original USRP one had 2 daughterboards on there because MIMO was a very important thing that I wanted to be experimenting with. And so it takes 2 daughterboards, and each daughterboard gives you 1 antenna. And so that would be 2 by 2. The newer devices only take 1 daughterboard, so you only get 1 antenna per motherboard, but you can get MIMO by linking multiple motherboards together. So, and the rationale behind that was that as we went to the newer, first a lot of people weren't interested in MIMO, and if we gave them 2 daughterboard slots, it was wasting a lot of hardware, and it made it more expensive than it would have to be, because there's parts on there that they're not using. So having 1 daughterboard per device sort of made it a little more efficient for the people who weren't doing MIMO, which is still the bulk of our users. And you get your MIMO by taking 2 motherboards and 2 daughterboards and linking them. The other real reason is because of pins. As we went to the more complex baseband chips, better A to Ds and better D to As, times when you double it because you have 2 daughterboards, that's a lot more pins, and the routing, and there's just not enough pins on the FPGAs. Each of our daughterboard interfaces today takes I think it's about 110 pins. If you put 2 on there, you now need 220 pins, and it's a lot harder to get that in a low-cost FPGA. Right. And we tried hard not to be pushed into the expensive FPGAs because that would really radically change our price points.
Right. Yeah, and that could even affect your connectors too. I mean, I've seen the high speed like mezzanine connectors that they sell these days. Those things, I mean, they go fast, and I'm sure you said they're 100 megahertz, 400 megahertz connectors or ADDs, right?
Mm-hmm.
So that means you're piping data back even faster if it's serial. And man, you have to start paying for a lot of connector space there too. I mean, obviously it's probably pales in comparison to the FPGA, but still, over the overall BOM, it can kill you.
Right. So in general, that's why we moved to the single daughter board per device. I will say in the future, we have a heavy emphasis on MIMO on the things we're working on in the future. And we will start to have multiple antennas per device again.
Okay.
But the sort of the generation 2 stuff that's out right now, it's one per.
Okay. So I wanted to get to a couple more listener questions before we're done here. Joel B. wrote in, the quality of a lot of code on sites like OpenCores is very variable and often poorly documented. The USRP uses a few, but it seems to be written from scratch by you. Is it faster to design as much from scratch so you can just understand how it works, or do you try and actually license modules where you can for any of these?
So so in particular on the USRP2 and our second generation stuff, when I first designed it, we made heavy use of the OpenCores stuff. We used the Wishbone interface so that we could hook up a lot of different OpenCores cores. The problem with that is, as Joel B says, they're very variable in terms of quality, and even when they're good, they're not necessarily targeted to what you're doing. So, for example, right now I think there's only 2 cores left that we have from cores. One is the ZPU, which is a very tiny CPU, and the other one is the I2C core. And I think the rest we rewrote ourselves. And the reason was, for example, with the UART, we had a UART core in there from OpenCores, and it sort of worked, but it was very heavyweight. It emulated a full 16C 550, and all that stuff, which, multiple baud rates, and you could do 8N1 or 7E1, and it was basically emulating an old IBM PC serial port. And really, we didn't need that. We just needed something to send, 9600 baud back and forth. And you can do that in about, maybe 20 or 30 flip-flops if you do it smart. Yeah. Whereas this core was actually taking up more space than the CPU was. And so, so it was a lot of the opens, they're great if they work for you, but you got to be careful. It helps to look at the author's name and know, sort of like, okay, this guy knows what he's doing. Some of them are written,
I also look at how recently they've updated it too. Yes. That one bit me once.
Yeah, a lot of those. Yeah, exactly. A lot of those on there are sort of somebody finished a project, uploaded it, and forgot about it. Just because they say it works doesn't mean it works. It's just because they say it doesn't.
It worked for me.
Yeah, yeah. And I've had ones that say, this probably doesn't work, but it actually worked pretty well. So you sort of have to know, the guy who's putting it up there. Also, some of them are just written for ASIC style, so they'll have asynchronous resets and things that aren't really efficient in an FPGA. So it's great in theory, but you just have to you have to look at it. You can't just sort of blindly use them. Yeah.
So are you guys pushing stuff back onto OpenCores now, or are you kind of keeping it in-house? I mean, excuse me, I was kind of curious just how the whole being acquired by National Instruments really affected you in terms of being a hardware maker, and also, how open are you guys allowed to be now because you are part of National Instruments?
Right. So we still produce significant code that's released under GPL for GNU Radio. So all of our GNU Radio work is still released under GPL, and we have. A significant fraction of the GNU Radio development is done within Edis Research. So we still do that. Our drivers are still open source. They're all GPL'd. Our FPGA code is still open source. So, I haven't pushed the cores that we put in our FPGA that I write or the guys here write. We don't necessarily push it onto open cores just because that's, that's like saying, well, why don't you put it on SourceForge? So we host it. we put it on our, it's all GPL, then anybody can get to it. They just won't.
Oh, okay.
They just won't find it on the Open Cores webpage.
Okay. So it's just geography.
Yeah, it's internet geography, really. It's sort of there. It's just easier if it's. I find it easier if there's one sort of canonical place to find the latest version of everything. And if we have a version there and a version on our site, it's just going to get out of sync. So, but yeah, all of our FPGA development, all of our software development, it's still all open source. And National Instruments never had any desire to change any of that. And that was a key factor to me in when I was determining whether or deciding whether we would say yes to the acquisition or would continue independently. And it was important to me that we be able to continue contributing and being a part of this open source community.
That's great. That's really. And so is the hardware open source as well?
So open source hardware is a nebulous term, and a lot of people have been trying to define it. So
yes,
I don't know.
One of them got dropped off our call, actually.
Right. So I'm not. Yeah. So I'll tell you what is open source. What is open source is the designs that go inside the FPGA and the all the software that we do and all of our drivers. That's all open source, and and we publish our schematics.
Oh, okay. So just you're not giving away board files. That's the only thing you're not doing.
Right.
Yeah. I see it as a continuum for that kind of thing as well. I mean, like that's a pretty good start. I mean, you're maintaining because you're actually manufacturing. I mean, that right? I mean, or is National Instruments manufacturing at their facilities, or how is that working?
So as of right now, we're still producing everything at the same contract manufacturer that we used to, which is actually just down the road from us in San Jose.
Oh, that's great.
So our newer stuff is going to transition to National Instruments manufacturing, but that's a sort of a slow process. So we are continuing with our existing CMs, but we've never done any, build in-house, right? We don't have our own assembly lines and stuff. We have
right.
our CMs do that. We do the testing in-house. So contract manufacturer builds the boards, puts them in the boxes, sends them here. We do all the testing before we ship them out.
Yep, sounds like a pretty standard contract manufacturing kind of thing. Just like Dave does, right, Dave? Is he back? Looked like he was back. Maybe he's not. Okay, well that's really great though. So what about the software integration then? I mean, I'm guessing National Instruments is interested in pulling your stuff in as a part of their software ecosystem. I mean, do you guys just kind of throw them an API, or I mean, you guys develop a lot of software yourselves as well. That's right.
Right. So from National Instruments' point of view, the users. So if you buy a USERP from us, it's directly from Edis Research. You're typically going to use it with GNU Radio or OpenBTS or with your own or MATLAB or Simulink or something else. If you buy it directly from National Instruments, you're typically going to be using it with LabVIEW. And National Instruments users work in LabVIEW typically, and so they have LabVIEW. So we have created, together with the folks in Austin, have created LabVIEW drivers for our hardware. And the LabVIEW driver actually talks to the UHD, which is our driver that we release to everyone. So we give everybody the same API. National Instruments builds on top of it. The MathWorks builds on top of it to create Simulink drivers and MATLAB drivers. And so GNU Radio builds on top of it to make the GNU Radio drivers. And so it's the same API, and so we handle all the sort of the hairiness and the sort of down and dirty details of dealing with the hardware within our driver, and then from the outside, it doesn't matter which of our hardware devices you use, it has the same UHD API, which stands for USERP Hardware Driver, and so the LabVIEW drivers talk to that, and all the drivers talk to the same API.
That's great, and that must work really well across all these. That's just a lot of cooperation too, especially for commercially owned enterprise. That's very impressive. I'm very impressed.
I mean, before we did this, we had sort of separate drivers for each of our devices, and they were it was messy. And so by going to this one API, which I guess we did about a year and a half ago, it allows everybody to just so you can write the same program. It'll talk to a usurp 1, a usurp N210. You recompile it. It'll work on your usurp embedded. And it's just made things a lot easier for everyone.
That's awesome.
Hey,
Sure.
Matt, can you hear me?
Welcome back.
I'm back. I've missed the probably half of the show here, but I've just raced to the office, and now I'm recording in the office. With the National Instruments, so this may have already been discussed, but with the National Instruments acquisition of you guys, what did you feel about that at the time? Did you feel, oh no, I'm being taken over by a monolith, or did you go, woohoo,
Go
yes,
monolith.
I'm, here's a great opportunity, you
Right,
know?
well-
What did you? Oh yes, I'm rich. I'm filthy rich beyond my wildest dreams, and I'm sitting on a throne of cash.
So I
as
was
Chris likes to say.
I was very lucky to not have needed to be acquired. So this acquisition, they approached me, and I made sure that it would be good for the company and good for the project before agreeing to it. I wasn't even really looking, or I didn't expect to be acquired until all of a sudden they showed up and said, "Hey, have you thought about selling your company?" I said, well, no, I hadn't, but I'm willing to entertain the offer. So, but basically, it was very important to me in the decision process to make sure that it was a company that was supportive of our vision. It didn't, National Instruments isn't going to become an open source company, right? But they saw the value in what we were doing. They saw the value in our community, and they saw the value in us continuing to be a part of that and continuing to contribute to the open source community. And so, and that was key. I would not have gone ahead with it if that was not, upfront agreed to.
So how do these acquisitions actually happen? Do you get a phone call out of the blue? Do, 5 guys in suits and baseball bats up at your front door and say, you're going to sell your company? Or
Dave has a really, really high opinion of it, obviously.
It was not, it was
Right.
not how I pictured it at all. First, I had been talking with some of these people at National Instruments for actually a while. I was trying to convince them to write LabVIEW drivers for our hardware. And so one day I got a call from the guy I had been dealing with. Matt, we should get together for lunch. I was like, okay. No, I thought, oh, they're going to write drivers, and I was really excited. And so we get to lunch, and I said, oh, well, considered selling your company, and so it totally caught me off guard. But I said, well, so we discussed it, and we went back and forth on numbers and culture, and I visited their offices and met a lot of people there, and was very impressed by the engineering driven culture of National Instruments. And that, because obviously it's a much bigger company. Today it's like 6,300 people in National Instruments. Yeah. Edis Research has 12. So it was important that we wouldn't get swallowed up in that we would retain our independence. Sure. And I felt that they shared a vision with us. So yeah.
Right. So that guy you had lunch with, was he authorized to do? Was he in a position to do deals, or was he empowered from higher up to sort of talk to you about it, or were you just dealing with a head honcho?
My understanding is so he was he sort of was the lead on this. He was the one who, and I didn't know about any of this at the time because they weren't telling me beforehand, but he had been following us for a while and sort of got buy-off, all the way up to the highest levels within the company. Once they went ahead and said, yes, we're gonna talk to them and make an offer, then he's the one who communicated with me. But during the process of it, I was talked to the CEO and all up and down the line, all the people. But he was sort of the point man on organizing it.
So was it easier than you thought, or was there a crap load of legal rubbish involved in being acquired?
It was there was a lot, but it was actually less than I expected, and it proceeded really quickly. I mean, they approached me, I think it was late October or early November, and we had completed everything by February 1st. So it was way faster than I expected. Part of that was because, we were a 4-person company at the time, and so it wasn't like we had to go through, I basically went out and hired myself a lawyer to handle this, but but it wasn't like there was big legal departments and
right, no shareholder voting,
right,
or anything,
and it was all very above board, and there was we didn't need to get buy-in from shareholders and VCs and stuff like that. It was so it was all relatively easy, and they impressed me as a very honest and above board company, and so it proceeded very smoothly. There was not nobody was yelling at each other in meetings and arguing over prices and stuff. It was remarkably smooth.
Well, that's another one in your column, Dave, for bootstrapping companies. I mean, it makes, if you do get acquired, it makes that simpler, and
exactly.
It's great. It sounds like it's really a great partnership, and that's impressive that National Instruments did maintain your culture. That's very impressive. You don't see that as much these days.
No, I mean, I know people who've been through sort of all levels of nightmare acquisitions where they come in and they clean the house, or they change everything you're going to do, or they tell you what to do, and really it's been the opposite of that. They've been more hands off than even I expected at the time of the acquisition. It's been very good.
Guys?
Well, I don't think it's that surprising though, because what would be the benefit them to come in and and hack it all up and everything like that? I mean, you're so small, there's so few people that you wouldn't want to piss them off, because then you'd just end up walking. So I don't see any advantage to them to come in and just and absorbing you in. Oh, you must come work here, and we're going to change the name of your product, and we're going to do this and that, and or we're going to discontinue it and just acquire your technology or something like that. That would be a bit foolish.
Yeah, I mean, I think that was clear during the process that everybody was on the same page and everybody wanted the same thing, and so I didn't, I was worried that they were going to come in and change things.
So I guess that leads to the obvious question is why they acquired you. Is it because they just want another subsidiary that makes money, or do they eventually have a longer-term goal to tightly integrate your products into LabVIEW and things like that?
So there's a number of reasons. I mean, so we National Instruments has a big focus, especially these days, on RF, and so and RF instruments all up to the very high end spectrum analyzers and automated test spectrum analyzers and that sort of stuff, all the way down to our sort of our cost points, and we represented a good way to get into those lower cost points and to fill out the product portfolio, and also they saw value in sort of what we had, and we've since we've made the LabVIEW drivers, and so it all everything works with LabVIEW, which is a key thing for National Instruments, and so you can run the same LabVIEW code with our hardware, or you can run it with the very high end spectrum analyzer. So it really positions National Instruments well in the RF space.
From the hardware side of things, the hardware and the production side of the hardware, do you find that National Instruments have or could bring about that could be helpful there, like have much more buying power, they larger volumes, that sort of thing, the price down and all that sort of stuff?
I mean, that's as we I'm not sure if you were on the call for this, but we talked about how we're still doing we have our local contract manufacturer doing our manufacturing, but as we transition stuff to National Instruments, that would be the hope that they have the economy of scale advantage, and also we're on some of our new hardware designs that we're doing right now. We're collaborating with them, and there's obviously with 6,300 people, there's a lot of resources there that we can draw on to enable us to create more with just our 12.
Yeah. Well, that's great. I'm really looking forward to stuff you guys are working on and seeing more stuff in the future. Any last thoughts before we kind of get running? We we know that you have places to be, and we really appreciate your time here.
No, it's been a lot of fun, and thanks a lot for the opportunity.
Great. So you can find Matt at edis.com. That's the Edis research page. Matt also has a Twitter account. I believe it's at Matt Edis. Is that right?
Uh-huh.
All right.
That's the advantage with having a more unusual name there.
If I could put in one plug.
Sure.
We are actively recruiting good engineers great engineers for FPGA design, hardware design, board level design, drivers, Linux drivers, low level code. So if you have any of those skills, and you don't have to have all of them, but if you're solid in any of those areas, please let us know, because we have about 3 openings right now.
Just sign up with the Amp Hour referral service, and we'll get them right over to you.
Mm-hmm.
The Amp Hour recruitment service. We specialize in this. We practically form the
Valve,
entire
Valve
hardware division. Yep. From all our guests. I'm surprised they don't. They haven't offered you a job.
Watch out, Matt. They might try and buy you away from NI or something.
Uh-oh.
I think we're up to 4
so.
now, aren't we?
Yeah.
4 of our guests have gone to the Valve hardware department.
Yeah, so
I can tell you the Edis research, jobs at Edis research are a lot of fun. So we try to keep it interesting here. So
that's
definitely,
great.
Can they contact you direct, or do they have to go through the usual boring as batshit channels?
They can send an email to either matt@edis.com or jobs@edis.com.
There you go, people. Jump
That's right.
the queue.
That's
this
the way
is how
to do
it works.
it, man.
This is how you get real jobs. You don't go through those recruitment consultant bastards.
We like it.
No. Go straight to the source.
All right, great.
Brilliant.
Thanks
Thank
again,
you very
Matt.
much,
Thank you, guys. Thanks a lot.
We'll see everyone next week.
See you next week.
Bye.